Everybody, welcome back. We're going to start talking more about data-efficient reinforcement learning today, but before we do that, we're going to start with a check your understanding. So this asks you to think back about what we were learning from multi-armed bandits. I would probably do 1 and 6 first, because they're kind of warm-ups, and then the rest of these. Just to clarify in terms of notation, I'm using f of delta here to be a function of delta, because I was slightly loose on exactly what the dependence is on delta in terms of whether, it's like delta over t or what we're going to choose for that function. So I just wanted to be agnostic to that there and put it as a log of a function of delta. As usual, feel free to look back at your notes from last week if you want to refresh your brain on the notation. All right, 1 more minute to write down your initial answers, and then I'll ask you to turn to a neighbor and compare. All right, why don't you compare your answers with someone that's nearby you? All right, great, let's come back together. So I think most people converged on the same answer for the first one, which is yes. Algorithms that minimize regret do also maximize reward. Ooh, hold on, pen is not working. Let's see if I can grab a different one. So the first one is true. I can get this on here. Okay, so the first one is true. If you minimize regret, you also maximize reward. For the second one, is that one true? Somebody want to say why it's true?
You say it's false.
I'm saying the second one is true. Hold on, let's see if I can get my thing to power up. My pen isn't working. So the second one is, just double check that I'll keep it back onto here in terms of the answers. I move things around a little bit last minute, which is always dangerous. But I wanted to include a couple additional ones. Okay, let's see if we can make this do the right thing. Okay, so the second one should be true. This is basically the UCB algorithm, which is this is the empirical estimate of the performance of each arm. So in the case where you just have a finite set of arms, which we can also think of as a finite set of actions, we just look at what their average reward was. NT of A was how many times have we pulled action A after T time steps. And log of F of delta was just the term that we had to try to express the dependence on delta. Delta was used to look at confidence intervals that we were using for the upper confidence bound. So this is true. The third one is also true. So in general, with our confidence intervals, you will be selecting all arms an infinite number of times, but it might be really slow later on because let's say you have a really big gap between arms, then that log term, and you'll have a T dependence in there in general, that will continue to grow a little bit, so you'll sample another arm again, which sort of helps with the fact that you might have been really unlucky and gotten a really weird estimate of the arm performance so far. Okay, this one was a little bit subtle, and I realize it could be not quite clear here whether I was asking you to think about the T over delta part or the 1 over square root NT of A. I wanted you to focus on the first thing. So what this is saying here is that instead of shrinking our confidence intervals by a rate of 1 over square root NT, we're shrinking them at a rate of n to the minus 4th. Let me just write that. That's very squeaky. Okay. All right, so let me just so we're shrinking it. So will that mean that our confidence intervals are wider or narrower for the same number of counts? So let's say versus NT of A to the minus 1/2. So for example, if NT of A is equal to 100, you've pulled this arm 100 times, which of these two is going to be bigger? The one on the left or the one on the right? That's right. So instead of it being, the other way around. So this is going to be, so if you have 100 to the minus 1/4 versus 100 to the minus 1/2, this is going to be 1/10. And this is going to be approximately 1 over 3. There's like several different inverses here, I know. What this means basically is that we're shrinking our confidence intervals slower. So another thing you might see often as a bonus term, DeepMind often uses this in particular for some of their algorithms, is to the minus 1. So that's a faster rate. So then that one would be 1 over 100. And you can think of these as trading off different amounts of sort of essentially how much exploration you're going to get. Because this is saying sort of how quickly are you collapsing your confidence interval as you have more data. Now, as somebody was asking me about when I was going around, they're like, well, we didn't just randomly pick this. We picked this because of the uncertainty bounds that we derived from Hofting. So Hofting said, if you have an empirical estimate of your mean, how far away could that be from the true mean? Well, under pretty mild conditions about your variable being bounded, we could get this kind of 1 over square root n rate. So someone was asking me very recently, well, why would you pick, say, this or something else? You might pick this because you just don't want to explore as much. So even though this holds for our theory, it's often somewhat conservative in practice. So you might just pick something like a faster exploration rate because empirically you want to just, explore less. And you could think of that as being related back to what we saw with PPO, that a lot of their theoretical derivation said this is what your step size should be, but it was way too conservative for most realistic applications. So they just changed it and they introduced the clipping thing. On the other hand, there might be cases for which you might not be sure you could get this sort of rate. And in those cases, or you might have other reasons to think you might need more exploration. So for example, maybe things are non-stationary and you think my customer preferences are actually changing over time. And so I want to sort of explore more over time than I would if I assumed that I was stationary. Okay, and we'll talk more about stationarity in just a second. So given all of that, this means that this expression would actually have wider confidence intervals and probably a higher upper confidence bound than our original algorithm, which means that we would still expect that over time, it will learn to pull the optimal arm, bless you, more than any other arms, but it probably won't have as tight regret bounds because we may be exploring too much. Now, this was an interesting one. Will this, if we add this particular bonus term, make the algorithm optimistic with respect to the empirical rewards? Somebody want to say if it's going to make, if we add on a bonus term, will it make it optimistic with respect to the empirical rewards? Just the empirical rewards, so like compared to your empirical mean. I'm not trying to make it a trick question, just.
Yes.
Yes, exactly. So if you just add 20 to your empirical estimate, it will be optimistic with respect to your empirical estimate. But is it guaranteed to be optimistic with respect to your true mean? So imagine if I'd said B was like 0.001. It would still make it be optimistic with respect to your empirical rewards, but would it necessarily be optimistic with respect to your true mean? In general, no, right? Like, so if you think back to our bandits, which just had binary rewards, let's say, you have a coin that actually has a 0.5 probability of getting a heads, which we'll call a 1. If you flip it once and you get a tails, your empirical estimate will be 0. If you add a bonus of 0.01, your empirical estimate will be 0.01. The true value of the mean is still 0.5. So one of the key ideas from using Hofting and explicit upper confidence bounds is that in general, it's not easy to figure out a simple bonus term you can add in order to make things optimistic. And so that's why you might in general want to be using these Hofting or other sort of explicitly derived confidence intervals. Okay, great. And then the last one is true. Does anybody have any questions about these yet?
Could you explain number 3 again? Because I'm not sure where the dependence on.
Where the t is at, it's inside of here. So if you go back to the slides from last time, let me see if I just have them up. Yeah, when we create these upper confidence bounds, so in general, we define these upper confidence bounds. We talked about how we need the bounds to hold over all time steps t. And so that in fact, this was not a perfect expression, that we're going to have some sort of t dependence inside of the log. And in general, we'll have like something like t or t squared inside of the log. And so that will introduce a dependence on the times, either the time step so far or your total time horizon inside of your upper confidence bound. Any other questions about this part? Okay. All right. I'll make sure that the solutions are aligned. Okay, so last time we talked about Bayesians, we talked about bandits, which were this single state version of Markov decision processes. your actions didn't make any difference to the next state because you're always in a single state. We talked about how people often use the word arms as an equivalent for actions. But there we were trying to be really explicit about uncertainty over the rewards. And we talked about an algorithm upper confidence bounds for trying to be optimistic with respect to that uncertainty. What today we're going to focus on mostly is Bayesian bandits, and we'll get there in a few minutes. Before we do that, I think it's nice to think about, I think it's exciting to think about all the application areas where these come up. And I wanted to go through this example, which I think I mentioned briefly in lecture 1, just again to think about all the complexities which come up when we want to try to use these in practice and where bandit algorithms in particular might be used. So this is a really beautiful paper by Hobsbawm Bastini, which was in Nature a few years ago. And they were trying to tackle a really important problem, which was at the time, as everything was shutting down with COVID, all these countries had to decide on a quarantine protocol and who to test. So before, a number of countries basically almost entirely shut down travel, but particularly in the beginning, people were letting, and even then often there might be, exceptions. So as people come into a border crossing, countries had to decide who to test. Now they couldn't necessarily test everybody because resources are finite. They're also having testing facilities they're using for testing all of their own individuals, and tests are expensive. In addition, when someone is tested, they were going to ask them to quarantine. Depending on where you were in the world, that might actually have been funded by the government. So you have to go to a quarantine hotel, which also costs the government money. So there are a lot of reasons in this case that your resources are limited and you don't necessarily want to test everyone. Also, in general, it may not be necessary to test everybody if you're trying to minimize the probability of letting in people that have COVID in terms of limiting spread. So if there's someone that's from somewhere where there's no COVID, then you don't necessarily need to test them. So this is the setting. What happens is that when people were coming into Greece, they would submit a form in advance, when you go to the airport or before you go, etc. And then what they would do is they had this approach called EVA, which tried to use the prior testing results to figure out who to actually test when they came. So what would happen is that then when somebody comes, like the next day, either they would say, we're not going to test you at all, and then you leave the premises, or for a subset of people, based on the form, based on where they were coming, and based on prior results they had, they would decide to test someone. Then, after you got that test, you would send it to a lab, and it normally would take 24 to 48 hours. I don't remember exactly what kind of test they were using there. Maybe it was some sort of rapid PCR. I don't remember. Those would go to a central database, and then they would use those results. So all these people would quarantine, for 24 to 96 hours or so during this time period. They would get the results back. If you're clear, you can go and proceed. Otherwise, you need to continue to quarantine. And then they're going to use this information to go back to EVA and update their algorithm. So this is really cool because this is an opportunity to try to be very careful about resources, but really do so in a way that still preserves the safety of the individuals in the country as much as possible and the public health. So I like that in the Bastini paper, they describe this as a non-stationary contextual batch bandit problem with delayed feedback and constraints. Okay, so that's quite a mouthful. But I think it's really nice to think about as we go from this simple setting of just thinking there are K arms, we can think about all the practical things that we might have to deal with in this setting. So here, in some ways, the K is very small. It's only 2. Either you're going to test someone or you're not going to test them. So it's a very small action space, which is nice. In this case, compared to what we've seen so far, but we'll see this case later, we're going to have context. Context you can think of as just being like states. So people will have a feature vector that describes what country they're coming from, a bunch of other details about them, and that gives you a state that we're going to use to decide whether or not to test someone. Okay, so that's why it's contextual. It's non-stationary because COVID was constantly evolving, and often a lot of the information we were getting was lagged. So if you're in Greece, you might be able to see information from Sweden and from China and from the US, but all of that information is often likely probably at a population level. Those people may or may not be the same people that are traveling to Greece, probably in general are different. because of the lag, it may or may not be informative. And in fact, in their paper, they argue a lot of that information was not as informative as this kind of real-time information. It's batched. What I mean by that is that, and we'll see this more today, you don't get to make a decision after every test or not test. You don't see the result immediately. So what happens here is that, say, 200 people fly in on a plane, you have to decide for every single one of them whether or not you're going to test them. And then you wait, 2 days. So it's this delayed feedback, and you have to make a decision for everybody before you get to observe that feedback. And so that makes it quite tricky, and we'll talk more about why that might be tricky for some of the upper confidence bound algorithms we've seen so far. I think this batching is really important for many, many application areas. So if you think back to our guest lecture and you think about direct preference optimization, this is another area where, in general, you're going to be able to get sort of a batch of data, label it all, and then continue. So in some of the work that my lab is doing and some other people's work, when we're thinking about doing adaptive data collection for preference optimization, we again need it to be able to handle this kind of much more realistic batch setting compared to getting information after each decision. Okay. We also have, so the delayed feedback is this 24 to 48 hours, and the final thing is constraints. So there are lots of constraints in this setting, which also generally change the setting from a lot of the ones we've thought about so far. So one is that you might have resource constraints. You might say at most we can handle, let's say, 100, I forget exactly what it is in the paper, 100 tests a day. So you're gonna have constraints on that. The second is politically you might have constraints too. It might be tricky for Greece if they decide that they're not gonna let in anyone from Sweden. So there might be different quotas, or there might be other reasons to say we have to think about some broader types of risks and benefits in these cases. So that's also challenging. One way you can think about implementing this is this could essentially change your policy class that is reasonable. So instead of your policy class saying you can make any decision for any individual, you may now have sort of a population level constraint as well. This is something that my lab has thought about some with our partner Sharad Goel, who's at the Harvard Kennedy School. And there we thought about cases where you might have resource constraints and fairness constraints that mean that you can't just make decisions for people individually, but you need to think about overall trade-offs in terms of your policy quality that happen at the population level. The reason that's important is because it often introduces a lot of challenges computationally when you can't just think of each individual separately. All right, so we won't be able to cover all of the ways that they handle this algorithmically, but I encourage you to read the paper if you're interested in this space. And I think it's a really beautiful example of using reinforcement learning, particularly multi-arm bandits, to tackle this problem. One of the things that they had to do, so this is a real system, they really deployed it in Greece. I think when I talked to Hafsa, she said it came together in like a month. It was a really amazing effort. And then one of the interesting things they also had to do here is to understand how much of an impact it made, because they weren't going to do a randomized control trial in COVID to understand this. So another interesting thing that this paper looks at is using offline methods, like the batch methods you've been seeing in the past, to try to estimate the counterfactual of how much impact this had. So I think it's a really nice example of a lot of the different ideas that we've been seeing in this class. All right, so that's one of the many, many ways that bandits are useful. Clinical trials is another one, A/B testing, ad placement. There's many, many others as well. But I think this is a really nice example in public health. Okay, so now let's continue. We're going to talk about specifically some of the algorithms that could be relevant to this, and in particular Thompson sampling, which is particularly relevant to this kind of batch setting. All right, I'm going to do very quickly just notation. Remember, regret is the opportunity loss per one step. Total regret is the total opportunity loss. We're using Q to denote the expected reward for a particular arm. So one thing, I'm blanking on who suggested this last time, forgive me, but someone came up to me and said, hey, couldn't we have used just like a smarter optimistic initialization? Do we have to actually have these upper confidence bounds? And I think that's a very reasonable suggestion, and that was a great follow-up to some of the stuff we're going to talk about today. So one simple thing you can imagine you could do, instead of worrying about these upper confidence bounds, which you have to update all the time, is you just initialize your Q hat to some high value. And then you just update that estimate over time. And when you do that, you know that eventually you're going to converge to the right thing. Like asymptotically with the law of large numbers, as you're not changing that initialized value. That initialized value may or may not have been right. It'll be an upper bound and it'll just converge to it. So this is an interesting thing you can do. The challenge with that is that in general, you don't know how high to make it. And so if you make it really high, now often, let me just be clear here what I mean by really high. Often this might be much, much larger than the actual range of possible rewards. So maybe your ARM rewards can be between 0 and 1, and you initialize this to 70. So sometimes, the initialization might be far higher than what is actually practical. It does encourage a lot of exploration early on, which might be really valuable. But in general, unless you get the value exactly right, which you generally can't know, because that's why you're trying to learn in the first place, then you can still lock onto a suboptimal action. And what do I mean by lock on is that you converge to a suboptimal action and then you never try anything again, which means you'd get linear regret. The other thing that's bad is that if you initialize Q too high, then you're also just not going to benefit from, you're going to be making bad decisions for much longer than you actually need to do. Okay? So even though in theory this could be a good thing to do, in principle you might imagine this is a good thing to do, in reality it's very hard to set. Now, it's also an interesting question of how you might do this with function approximation. So if you think back to, I know you didn't implement deep Q learning, but if you think back to deep Q learning, where we used a neural network to represent the Q function, do you guys think it is easy to initialize that so the values are optimistic? I see at least shaking his head. Why not?
It's just
You're right.
The network to output a specific value.
Yeah, it's hard, right? Like maybe you could train it on fake data, but then you'd have to know how big the Q is. Yeah, in general, this is really, if it was a table, it's at least easy to write down, like 90 for all of those things, and that's what you initialize. In a deep neural network, it's really unclear how you initialize those parameters so that for all the states that you would reach, you would have even a good shot of it being optimistic. So I think that's another challenge here is, and that's a challenge for a lot of the optimism algorithms we'll see in general is, can we do it with function approximation? Now there's a lot of work on thinking about sort of how to do things with function approximation, and we'll get into that soon. Okay, so if you do carefully choose the initialization value, you can get good performance under a new way of measuring what good performance actually means. Okay, so let's go back to regret. So in regret, we sort of just try to think about how do we quantify the performance as we make lots of decisions. So T here is the number of decisions we make. And we're just trying to think in this case about how many decisions we make over time. Let me see if the pen is finally charged. Not today. Okay, so we could either be making lots of little mistakes or infrequent large ones. And what you might imagine that we want to do is to think about a different form of loss. And so, or in particular, another form of performance, and that is going to be pack. Okay, so let's draw what that'll look like. Okay. So, I think I drew this last time, but I'll draw it again. So I make this time step T, and this is Q of AT, Q of the actual arm that you pulled, and this is Q of A star. So let's imagine that you have an algorithm that is pulling arms like the following. Okay. All right, which means that, then maybe sometimes it's pulling the right arm, hopefully. Okay. So in this case, sometimes the algorithm is doing something that's just a little bit suboptimal, and sometimes it is making a really big mistake. So what we can do here is we can quantify how big our mistakes are. And you might have a situation where you say, optimal performance is really hard. You know, it's really hard to learn like what everyone's perfect like ad preferences are, things like that. Maybe I'm going to relax my criteria. I'm not going to require optimal performance, but I want pretty good performance. I want epsilon optimal. So what we do in this case is we count every time we make a bad decision, meaning something that is worse than epsilon optimal. And otherwise, we think of all of those as basically being in an equivalence class of optimal. So that's going to be what we think about when we think about PAC. Okay, so I'll define what that is. So a PAC algorithm, and raise your hands if you've seen this in machine learning. If you've taken machine learning, you might have seen PAC. Okay, yeah, so at least one or two people have. So often in machine learning, particularly if it's a machine learning class that includes some theory, they'll talk about PAC and probably approximately correct algorithms, and that's where this idea comes from. So it came from the machine learning community, and then reinforcement learning borrowed it. So the idea in a PAC algorithm is that on each time step, a PAC algorithm is going to choose an action whose value is epsilon optimal, meaning the value of the action that's taken is at least the value of the optimal action minus epsilon. So that means that we're in this region, with high probability on all but a polynomial number of time steps. So essentially it's saying that the majority of the time your algorithm is making good decisions. Good here being defined as epsilon optimal, but sometimes we'll make bad decisions. But we're going to say with high probability, the total number of bad decisions we make is not too many. What we mean by not too many here is something that's polynomial in your problem parameters. So that generally means like the number of actions you have, epsilon, delta, etc. As you might expect, if epsilon is smaller, generally the number of samples you need will go up. Normally something like 1 over epsilon squared. So if you care about being more optimal, you're going to need more data. Or in other words, your algorithm might make bad decisions for longer. If delta is smaller, meaning that you want this to hold with higher probability, you'll also need more data. And if there are a lot of actions to learn about, in general, you need more data. So it gives us some notion of sort of the complexity of the problem to learn in. So this is a different type of, a lot of algorithms you can get both PAC guarantees for and regret guarantees, but it is just a different notion of optimality. Okay. Most of the PAC algorithms for reinforcement learning are based on either optimism, like what we've seen from last lecture, or Thompson sampling, which we're going to see later in this lecture. And there do exist PAC algorithms that just initialize everything to a really high value. I don't know of any practical algorithms that do that, like ones that people use in practice, but there is theory and papers about that case, so it is possible to do. All right, and we'll see more stuff about PAC shortly. Let me just give an example. So remember back to our fake trying to learn how to treat broken toes example from last time, where we had surgery and taping, like buddy taping the toes together and nothing. Again, this is not medical advice. Imagine that this is epsilon is 0.05. So in this case, before we thought about this is what the optimal sequence of actions you should take, but of course you don't know that because you don't have data. If you had this sequence of actions, say under an optimistic algorithm, this would be the regret you would get in each case. But under the PAC case, let's see if I can type these here. Under the PAC case, this would be okay. So the important thing to notice here is that because the reward of A2 is within the epsilon bound of A1, which is the optimal action, this action would also be considered optimal. So from the perspective of the PAC algorithm definition, this would be not denoted as a mistake. The only mistakes would be when the algorithm takes A3. So when we talk about this PAC definition here, of sort of counting up the number of time steps we don't make a really good decision, the only decisions that would count for that in this setting is the A3 decisions. In contrast to that, when we talk about regret, anything that's suboptimal counts. So you get penalized for all the A2 decisions.
I thought we were allowed to make mistakes for a polynomial number of steps.
Yes, but I guess yes, you are allowed, and it still will be packed. That's exactly right. But I'm just pointing out here that the only actions you're taking that count towards that polynomial is A3 here. It's not A2. Whereas A3 and A2 count towards your regret. Yeah.
Does training become easier if I gradually reduce epsilon?
Good question. So normally in these cases, you fix epsilon in advance, and it defines kind of it defines the number of samples you're going to need for each of the actions or states and actions in the MDP case. So it's kind of like an exploration term, and you keep track of counts. There are algorithms with me and my former PhD student. Part of the work that we did there was to talk about what if you want to have guarantees over many epsilons at once.
I'm thinking more along the lines of epsilon greedy algorithms we did in RM, where because we gradually reduce epsilon, we converge to the optimal policy. Does the same, can we use the same thing there?
Yeah, it's a little bit subtle. It's a great question. So in general, the bounds will depend something like 1 over epsilon squared. So if your epsilon is going to 0, that will say that you have to do an infinite amount of exploration. If you're interested, I have to send you one of our papers thinks about trying to have sort of simultaneous bounds over lots of epsilons. But in general, the basic version of this, you commit to an epsilon in advance. Great questions. All right, so going back to sort of where we are and reminding ourselves in terms of algorithms, this relates to your epsilon greedy, constant E-greedy, decay E-greedy, and optimistic initialization all have the problem in general of having having bad performance. It's in theory possible to have sublinear regret, but you often need to have stronger knowledge than is known. Optimistic initialization also can have the pack guarantees that we just talked about. And I guess I'll just say too, you can convert these results into, so epsilon greedy is not a pack algorithm, but you can think about different types of other sort of exploration strategies and whether or not they're pack. And we'll get back into those soon. Okay, let's jump into Bayesian bandits. They're a pretty elegant idea. So far, we've made almost no assumptions about our reward distribution. So we've maybe said they're bounded, it can be between 0 and 1, and that's basically all we needed for Hofting. We need them to be bounded, we needed them to be, we used that they were independent and identically distributed. But we haven't made any other assumptions. So we haven't said it's Gaussian, or it's a Bernoulli, or something else we might know. And when we're being Bayesian about this, we're actually going to leverage knowledge we have about the structure of the way the rewards are generated. And what I mean by that is normally some particular statistical model. So it's a Gaussian model, or it's a Bernoulli model, things like that. And the reason that that might be helpful is that often if we're doing these in a domain, like public health or others, people might know lots of information about what the reward structure is, bless you, and could we leverage that to get better algorithms and better performance? Okay. So before we do this, it's probably helpful to do just a quick refresher on Bayesian inference. Some of you guys might have done a lot of this, some of you might have done very little. We'll go through sort of just a quick reminder about this. Okay. Because this is going to be used a lot for what we're going to see today. Okay, so the idea is that we're going to start with a prior over the unknown parameters. In our particular case, that's going to be the unknown distribution over the rewards for each arm. So it's like if we have a coin flip, or like if we think about the toes example, what's the probability that someone's going to heal if they're given surgery? We don't know what that parameter theta is. And so we're going to have a prior over what that theta could be. Once we're given some observations about that parameter, for example, if we observe when you do surgery that someone was healed, that is going to change our uncertainty over the unknown parameters. Okay. So let's do a particular example. So if the reward of arm I is a probability distribution depends on a parameter phi I, we have initial prior over that parameter. Pull an arm, we observe a reward. Then we can use Bayes' rule to update that. Okay. And I think it's really helpful to visualize how the priors change over time. So we'll see that in an example shortly, just so you can kind of see what that might look like. Okay, so what we're going to have here is Bayes' rule. Okay. All right. This is our prior probability over the parameter governing the reward distribution for this arm. This is the likelihood of observing a particular reward given a specific parameter value. And this is the probability of seeing that reward in general. Okay. And when we do that, this is Bayes' rule, and then we use it to update what our new probability is over the parameter that generates that reward. So in the case of surgery, it would be before we had some distribution over how successful we think surgery is on average. We give surgery to someone, we update it, we observe that they are healed, and then that changes what we think about the underlying parameters. So, written that out here. So this is the prior probability, this is the probability of reward given a particular parameter, this is the probability of getting the reward in general, and we can rewrite this by using the joint distribution of the reward and the parameter, and then marginalize out the parameter. Okay. All right. Okay. So this is beautiful and really, oh yeah.
Can we go back to the last slide? I'm just kind of confused on the setup. Like, if I imagine that phi is like the parameter for like a Bernoulli variable, and using like background knowledge, I have some sort of prior as to what this should be. Like, what does it mean to have a distribution over that?
Yeah, it's a great, so it's, in general, it may not be obvious that we can compute this. So for example, we're going to see in some cases this is analytic. You can analytically update this, which is super elegant. What I mean in that case is like, as a simple, so let's say, we'll see an example shortly. The phi could be, is the probability of recovery. I'll do this for surgery. Okay. So this would be saying like, 90% of the time someone's recovered. And let's say, or something like that, right? And this could be a particular prior. Okay. So I could say, I think my probability that you're recovered mostly from the surgery is 0.9. So I'm pretty confident that the surgery is going to be highly effective on average. But, I think that there's some probability that the surgery is not so effective. And then I would say, well, I think that, maybe with 10% probability the surgery isn't as effective, but on average, people are going to recover at rate 0.4 with the surgery. And we'll see some specific examples of this. This is not the priors we're going to use, but this just illustrates how you can have distributions over distributions, which can get confusing pretty quickly, but on the other hand is also super elegant and a place we can put in prior knowledge. Because like clinicians and others may have information where they can actually directly specify these sorts of priors. All right, and so there's many questions you might have in this case of like, where do these priors come from? And even if we have these priors, how do we do this calculation? Okay, so in general, this is complicated. So you can see here, you've got to have like a functional form for this. This in our case was like flipping a coin. And so if your coin has a bias of 0.9, what's the probability you'd get reward 1? It would be 0.9. So you have to have probability distribution here, probability distribution here. You have to marginalize one out over here. And when you do all of that, you get your new posterior, which is after you observe something, now what is your new distribution? So you might imagine that now I update this. Maybe I see that the surgery was successful and I'm like, oh, well, maybe I'm going to update this to be 0.95 and 0.05. Okay. So in general, this is going to be computationally tricky to do exactly without additional structure. There's lots of ways to approximate it, but the really cool thing is that in some cases you can do this analytically. So this is this idea of these conjugate priors. So there's this beautiful idea of the exponential families. And if you have a representation of your prior that is conjugate with, this is often called your likelihood function, then after you do all of this updating, this new thing is in the same statistical family as what this was in before. And we'll see some specific examples of this in a second. So the high level, really beautiful idea in this case is that it's analytic. When you do all of this, let's say this was initially like a Gaussian, this is still going to be a Gaussian if you use conjugate priors. Okay. So let's see how to do this for Bernoulli. So for Bernoulli, there is a conjugate prior, which is really cool. And the conjugate prior is called a beta distribution. And it's going to have a really nice, beautiful interpretation that we'll see in just a second. So the equation looks terrible. The equation says the probability of a particular theta, remember this is like the bias of your coin, given some alpha and beta, these are just two other parameters, is theta to the alpha minus 1, 1 minus theta to the beta minus 1, times the gamma function of alpha plus beta divided by gamma of alpha, gamma of beta. Okay, so this looks fairly terrible, but it is conjugate, which means that after we observe something, our new posterior is also going to be the same. But it turns out that it has a really simple explanation, a really simple intuition, which is, imagine you start with your prior being a beta, alpha, beta, and then you observe a reward that's either 0 or 1, because your variable is just 0 or 1, it's a Bernoulli. Then your new beta, your posterior, is just r plus alpha, comma, 1 minus r plus alpha. What does this mean? If you observed a 1, then you increment your first parameter. It's like you increase the number of successes. If you observe a 0, you increase this number, the second number, like you increase the number of failures. So you can think of what the beta is doing is essentially just keeping track of how many heads did you get, and how many tails, or how many 1s did you get, and how many 0s. And it's just keeping track of those, and it can use those to explicitly update what the probability is of your theta. Okay, so it's really beautiful because you don't, computationally, that's really easy to keep track of. I'm just going to add 1, if I know what you've seen. And what you can think of this here as being is how confident are you in advance of sort of how many pseudo counts did you see of success versus failure. So for example, if I'm really confident that the surgery is going to be successful, maybe I'm like, yeah, I'm so confident it's as if I've seen 100 successful surgeries and only 2 failures. Okay. But if I'm really uncertain, what I would do is I'd say, well, I'm going to treat it like 1 successful, 1 failure. I really don't know. And we'll see what this looks like in just a sec. Okay. Excuse me. So now when we have this, this is basically giving us a distribution over the reward parameters, and we can use this to actually make decisions. All right. So there's a couple different ways to do this, and one of the ways to do this is by getting a confidence interval, similar to what we've seen before. But the other thing is called probability matching or Thompson sampling. And let's go through Thompson sampling now and see an example. Okay. All right. So in probability matching, we're going to assume we're in the Bayesian bandit case. And what probability matching does is says, okay, the way we might want to explore is by sampling actions according to the probability that they're optimal, given everything I've seen so far. Okay, so what it says is, given some history, which is like the past things I've tried and whether I've gotten 1s or 0s for them, I want to select a new action based on the probability that its true mean is higher than the mean of all the other arms. And I'm not going to tell you yet that that's, formally a good thing to do in terms of regret, but you might imagine that's a reasonable thing to do. It sort of says like, oh, well, if I think that arm is likely to be the optimal one with 60% probability, I'll try that with 60% probability. And then if I think there's another arm that might be optimal, I'll try that with, 30% probability. Now, in general, it's not clear how you would compute this. It seems like kind of an interesting idea. It's not clear how you can compute it, but it turns out there's a really simple algorithm to compute this. So this is called Thompson sampling. And I think it was first invented by Thompson maybe in 1919, maybe 1919, maybe 1920. No, 1919, Thompson sampling. Okay, so it was around forever. I mean, it's been around for like 100 years. But at least from the machine learning perspective, I think it was forgotten about for like the first, 90 of those. It really came back into prominence about 2010, 2011, when some people discovered that it actually had some really nice empirical properties. So unlike Hofting, which has been used for a long time. How does Thompson sampling work? We're going to have a prior over each arm. Then for each iteration, what we're going to do is we're going to sample a reward distribution from the posterior. We'll see an example of exactly what I mean by that. We compute the action value function, given that sample. We take the arm that is maximum, given those cues. We observe a reward, and we update our posterior. And then we're going to do this many, many times. And again, this will all seem much more concrete when we do an example. right? And it's going to turn out that this exactly implements probability matching. So let's come back to this in a second, and let's first do a specific example, because I think that'll make it a lot more concrete. All right. So let's go back to our broken toes example. What we're going to do, so we're going to place a prior over each arm's parameter, and I'm going to choose beta 1, 1. What does a beta 1, 1 look like? That looks like the following. And I'm sorry my pen isn't working today, otherwise that would have been helpful, but I'll draw it up here. Okay. Okay, this is 0, this is 1, this is theta. Okay. We know that for a Bernoulli variable, the value for a theta has to be somewhere between 0 and 1, because you can either always get 1 or always get 0 or somewhere in between. What a beta 1, 1 looks like, so this is going to be the probability of theta. This is my prior. What a beta 1, 1 looks like is this, which is a uniform distribution. What it says is, I have no idea what theta is. It could be 0, it could be 1, it could be 0.5, it could be 0.7, it could be 0.9. It just says someone is totally agnostic. This is called often like an uninformative prior. Saying I have no idea what my probability is for surgery, etc., but this is what that looks like. Okay. So this is our prior. And now what we're going to do is we're actually going to sample a Bernoulli parameter, given the prior of each arm, for the 3 arms. Okay, so what does that mean? That means I'm going to sample something for surgery. I'm going to sample something for buddy taping. And I'm going to sample something for nothing, for do nothing. All of them have this particular prior for now. So for the first one, it's like I'm just sampling from a uniform distribution between 0 and 1. So it could be anything between those 0 and 1. Okay, let me just check which number make sure I use the numbers that I'm going to use for the next ones. Okay, so let's say, for example, that I happen to sample 0.3. Okay, that's a totally reasonable thing that I could sample given this uniform distribution between 0 and 1. Then, for buddy taping, let's say I sample 0.5. Okay, again, a totally reasonable thing I could sample given this distribution. And for do nothing, I'm going to sample 0.6. Okay. So this is just the distributions that I have over my prior over the parameters. And this is a particular set of parameters I could sample. Given that, what Thompson sampling says I should do is I should select the action that is maximal given the parameters I've sampled. So under these 3 parameters, if you want to maximize the probability that someone will recover from surgery, or sorry, recover from in terms of their broken toe, should I do surgery, buddy taping, or nothing? Which one has the highest chance?
In this case, nothing.
In this case, nothing, right? So as soon as in our case, it's pretty simple once you see the theta, because the theta is exactly equal to the expected reward. So what this would say is, in this case, you should do nothing. So this is going to be okay. So this will say do nothing. All right, we're going to observe the patient's outcome. Now, in this case, we're going to assume that doing nothing is actually not so effective, and so we're going to observe a 0. And now what we're going to do is we're going to update the posterior over doing nothing, given that observation. Okay. Now the other two arms, their prior hasn't changed because we haven't gotten any observations about surgery or buddy taping. The only thing we've got an observation about is doing nothing. So what I said before, so we have alpha, this is our alpha beta parameter, so this is our prior. In particular, it was beta 1, 1 before. And when I pull this arm and I get a reward of 0, what I said we would do here is the first one you can think of as being the number of successes, and the second one is the number of failures. So what this becomes is it becomes beta 1, 2. Okay? And that is going to look different. It's going to look like this. This is a beta 1, 2. And this is a beta 1, 1. Okay. Does somebody want to tell me intuitively why it makes sense that this looks like this for doing nothing? Where does this put weight in terms of parameters?
Since we received a 0, we should think it's more likely to be 0.
Yeah, we should think of the parameter value as likely lower. And so we've shifted our probability mass. And so we're like, okay, for the things that we don't know, we're still totally agnostic about whether they're effective or not. For the things that we just tried, do nothing, we got a 0. So it is more likely that our actual theta is lower. Because a lower theta, in general, will generate more zeros. And so we've changed our distribution. Let's see what that looks like here. So this is our new posterior. We're using, again, remember this is conjugate. So this is our new beta. And we haven't changed it for the other two. Now here's the next important thing. What we're going to do now is so this is what that beta looks like, just for beta 1, 2. Now we're going to do our next step at Thompson sampling. So what we have to do now is we now have to resample. So we're going to resample where we have two distributions. These two ones are a beta 1, 1, and this one is a beta 1, 2. Okay. We're going to throw away all of our old parameters from last time. They were just samples. We now have an updated distribution for one of the arms, and then we have the old one for the other two. So in this case, we might resample and we would get this. It's more likely now that we would sample a theta 3, which is lower, because our beta puts more weight on the lower part. Okay. So this is what this looks like here. So under this, we're going to pull arm 1 because it has the highest expected success. And that one is going to give us a beta 2, 1. Because remember, again, that we increment the first one in terms of the number of successes, the number of failures. So as you might expect, it's exactly symmetric to this one. And we have something that looks like this. I'm not being perfectly precise of the intersection. So now we can, again, we throw away all the old parameters that we've sampled so far. So we're going to throw away the 0.7, the 0.5, and the 0.3, and we're going to resample. Okay. So this time, let's imagine we sample like 0.71, 0.65, and 0.1. And we again observe that the outcome from surgery is successful. This is what a beta 3, 1 looks like. So it stops looking like a straight line. It starts having a curve. So I really like these graphs because I feel like it gives one a much better intuitive sense of how, as you get information, that translates to your posterior over what you think the theta likely is. So as you see more successes, it'll tend to go weighted to one way. As you see more failures, it'll weighted to the other way. And as you might expect, so we're not seeing that right here, but if you can see cases where it starts to concentrate in the middle or somewhere in between, right? Just depends on what actual observations you're getting. Okay. So this is how Thompson sampling works. And I think, so let's say we did this, then now we have this something that's even more peaked, we get another one, and you can see it just continues to curve. Okay, yeah.
Could you use Thompson sampling with like random variables that are just like have many more parameters, like as opposed to just using Bernoulli's?
Yes, absolutely. Yeah. And one of the examples we'll see later today, they're using it for advertising and they have a large number of features. Yeah, you can extend all of these to the function approximation case. Good question. Okay. So I think one of the things, I mean, obviously this is a small example. What we saw in this particular example I just did is that we quickly started to converge to a 1 in this case. Now notice so far we've actually never pulled A2. We had some probability of pulling A2 because if we had sampled a really high value for A2, then we would have pooled it. But we haven't done that yet. And A1, which actually does have a high, like generally a higher probability in this case of having good outcomes, is starting to be pooled. So it's quite different than the optimism methods, because in optimism we had to at least pool each arm once, so we could even start to initialize our confidence bounds. That's not the case here. We already have a prior over what the values are, all of these, and we can immediately start using that to make decisions. Okay. All right, so what is Thompson sampling doing when we're doing these pools, and what sort of results do we have in this case? So what it is doing in this case is actually let me just step back because I wanted to get to the example, and then, so I went through that part a little bit fast. Let me just go to how the matching is working. So let's just go back to here for a second. So what we can see in this case is what Thompson sampling is actually doing is at each time point, it is trying to select actions according to this probability. Yep. And it'll often end up being optimistic in the face of uncertainty because we're doing an argmax with respect to like our empirical estimates. But it won't, in general, as you might imagine, uncertain actions have a higher probability of being the max. So if you are really sure that your parameter is at 0.5 and you have another parameter you have very little information about, like you have a beta 1,1, then you're more likely to accidentally sample a much higher value for that parameter. So the elegant thing here is that you can think of this as the following, and this is really useful also for the theory. So in posterior matching, that's this first line. That's sampling things according to this. What Thompson sampling does is it doesn't do that explicitly. It just samples a reward for each of the, like a reward parameter for each of the different arms, and then it picks the one that's argmax. And so it's really elegant that that is, in fact, the same thing as doing probability matching. Okay. That gives us the fact that that ends up working in terms of these. So the key idea in this case is that as you're computing these with respect to the data that you have so far, in fact, the probability that Thompson sampling picks an arm is exactly equal to this true probability given all the data you've seen so far. I'll do a pointer. If we have time at the end, maybe I'll go through the proof briefly for the Bayesian regret case. But there's also a really nice explanation of this inside of Tor Lattimore and Chebyshev Aspari's book. There's quite a lot. There's a quite mathematical version of it, but it gives you some really nice background. Okay, let's go back to here. Okay, so let's first just talk about how do we evaluate performance. So what we saw in frequentist regret, like what we saw last time, is that we're assuming like a particular unknown set of parameters. So like our arms are actually 0.9, 0.7, 0.6. We just don't know what they are. And then our regret is always evaluated with respect to the optimal arm given that fixed set of parameters. Bayesian regret assumes there's this prior over the parameters. And so when we talk about regret, we're actually taking an expectation with respect to that prior. So it's still, this looks like exactly the same as the frequentist regret, but now we have this outer expectation over theta. One of the key ideas of this, in terms of how one might prove things in this case, is if we think back to how we proved some ideas around regret. We didn't do the full proof, I just tried to give some sketches. One of the key ideas in the proof for frequentist regret and upper confidence bounds is that we tried to construct these upper confidence bounds UT that we thought would be higher than the true value of the arm with high probability. And we used that in order to figure out how many times we would pool suboptimal arms. We leveraged sort of this fact. So it turns out that you can do Bayesian regret bounds under a pretty similar decomposition. You can think about sort of computing an upper confidence bound and the likelihood that it'll hold. We might come back to that later today, but I want to first sort of get into extending these up to sort of higher level settings as well. Before we do that, I just want to highlight that if you try to get standard bounds, like what we saw last time for standard Thompson sampling, and what I mean by that is the type of Thompson sampling I just showed you, to my last check, they don't actually match the best bound for like upper confidence bound and frequentist algorithms. However, often empirically, they can be really effective algorithms. And I'll just highlight here that in general, you can't compare directly between Bayesian regret bounds and frequentist, because one of them is with respect to this prior over parameters. Okay, so let's look at that for a particular domain and why Thompson sampling might be particularly helpful for a lot of real world cases. So this is a really nice paper by Olivier Chappelle and Li-Hung Li, which sort of initiated a huge amount of interest in Thompson sampling a little over a decade ago. So I think they were both at Yahoo at the time, if I remember right. They were thinking about a contextual bandit case. So they were thinking about making news article recommendations, et cetera. And so there you would have a context, like you'd have a bunch of features about an individual, and also often you would have a bunch of features about the arms. So like explaining like they'd be news articles and all the features, or ads and stuff like that. But we're still going to assume the context is sampled IID at each step. So if I give a particular ad at this time point, it doesn't impact what's going to happen to. Okay, so it's still a bandit. There's no like sequential dependencies there. Arms are articles. Reward is binary. Either you click on it or you don't. In this case, you can model it using like logistic regression because you have this binary output. So what are we seeing here? So this is CTR, which means it's a click-through rate. It's normalized because they're not going to tell us exactly what they get on their real-world data. The important thing to look at here is the x-axis, which is delay. So in many cases, just like what we saw for the public health setting, there'll be some form of delay, even for online customer cases. So Amazon will show you something and they don't find out for a little bit of whether or not you're clicking on it or whether you bought the thing. And so what they're comparing their algorithms with here is the following. So TS is Thompson sampling, OTS is optimistic Thompson sampling. You can try to add in a little bit of optimism in these. UCB is upper confidence bound. EG, I think, is epsilon greedy, and exploit is you just do whatever the mean looks like so far. These are all hyperparameters. As often is the case, the hyperparameters matter, so it's useful to look at these. I think the really interesting thing to look at in this case is to look across the time. So this is sort of the shortest delay, and this is the longest delay. And you can see for the blue algorithm, it varies very little in terms of its performance, even if things are delayed a lot. But if you look at, say, UCB, its performance tends to drop a lot in terms of as you have longer delay. Okay? And so that is one of the reasons why you might want to do Thompson sampling in these cases. Okay? So let's think more about that, okay, and check our understanding. So let's think about an online news website with lots of people logging in every second. Often someone will come online before you've seen the outcome of the previous person. It asks you to select all of the things that you think are true as we think about Thompson sampling versus upper confidence bounds. All right, why don't you compare your answer to someone nearby you? Okay, so let's come back together. So as we were just discussing, pointed out that like Thompson sampling could cause much worse performance. This one is true than optimism if the prior is very misleading. So this is true. Okay, because if for example, maybe surgery is really effective and someone starts off and thinks surgery isn't effective at all, and so you put a lot of probability mass, you could have a really sharp prior on it over here, then it could take a long time essentially for your data to overwhelm your prior. So this one can be a problem. The first one is also true. So if you think back to the algorithms that we saw last time for optimism, there is no randomness in there unless you have a tie. So if your upper confidence bound for arm 1 is higher than the upper confidence bound for arm 2 and arm 3, you're just going to take arm 1. And that's fine, but if you have a delay, that means you can't update those upper confidence bounds. So if like the next customer comes, you're like, oh, or like the next patient comes, you're like, I still think surgery is best. I still think surgery is best. And you're not going to try anything different. Whereas Thompson sampling just has this prior or posterior. And so if I have someone come, I can just sample from all of my, my priors. And then if another person comes, I'll again sample from my priors. And so because of this sort of distribution over parameters, unless it's collapsed to a delta function, in which case you know what the right thing is to do anyway, you'll get natural exploration. So that's one of the really big benefits of Thompson sampling, is that even if you don't get new data, you naturally sort of will try out different things, and that can be really helpful. It is true that optimism algorithms generally are better than Thompson sampling in terms of their regret bounds. That may or may not translate to empirical benefits, but they don't actually necessarily have stronger regret bounds for this setting. So this is false. And that's because all the bounds we've been talking about so far don't think about that batch setting. They're being derived for the case where you get information, you update your confidence bounds, you continue. So this sort of highlights some of the particular benefits and the potential weaknesses of Thompson sampling. If your prior is reasonable and you've got this sort of delay or batch setting, it can be very helpful. If your prior is really bad, that it can take a long time to sort of get past that. So before we end today, I think an interesting question to consider is whether or not Thompson sampling is optimal. Now, we can get nice regret bounds for this case. I know I didn't have a chance to go through that particular proof today, but it's not optimal in general. So it would be really cool if we could get something that was basically perfect. You might imagine that if you have a prior and you have a known horizon, that you could compute a decision policy that would maximize your expected rewards given that prior and the horizon. So I haven't, at least in this class, taught you all the tools you'd need to do that, but at a high level, you could think of it as kind of a Markov decision process over parameters, which is kind of wild. So if any of you guys have taken Michael Cockendeffer's class, actually, who's taken Michael's class? Anybody here? Okay. So you can think of it like a POMDP. Your state is your parameters, your actions are pooling things, and then your belief state is your new probability of your parameters. So it's really elegant. In theory, you can compute something that will exactly maximize your expected reward by doing POMDP planning. The problem, also for those of you who have taken my class, is that often POMDP planning is really intractable. So it's often not clear that we could do this in a computationally reasonable way. In general, one of the challenges here is that if you wanted to do this, it would have a decision policy that's a function of the history, which means all the prior actions you've taken and all of the rewards you've observed, and that's going to increase exponentially with the number of decisions you made. So there's this idea of an index policy, and an index policy says we don't want to have to think about this exponential sort of history or state. And an index policy is a decision policy that computes a real valued index for each arm, and it plays the arm with the highest index, using statistics only from that arm and the horizon. So that means I don't have to pay attention to this sort of combinatorial exponential thing. I can just say, for this particular arm, maybe, what were my rewards that I've observed so far, and then I can use that information to make decisions. So for example, a greedy algorithm, which just relies on your empirical average of the performance for each arm, is an index policy. So is an upper confidence bound algorithm, because it just relies on the upper confidence bound for the rewards you've seen for each arm. So there are a lot of index policies. Surprisingly, there is an index policy that is optimal. So Gittins proved that there exists an optimal policy for maximizing the expected discounted reward in a Bayesian multi-arm bandit that you can compute that only depends on these statistics separately for each arms. So that's really cool. It means that it is possible in some settings to actually exactly optimize your expected sum of discounted rewards for these type of Bayesian bandits. Thompson sampling will not do this in general. So Thompson sampling is generally not equal to what the Gittins index would be, but it can still be a very good thing to do. All right, so just to summarize some of the things that are useful to understand from this part of the section, and next time we're going to start talking about these sort of ideas for sequential decision processes, like Markov decision process. You should be able to define, regret, and pack. You should be able to prove or know why sort of the UCB bandit algorithm has sublinear regret, like up to the proof sketch we did in class. You should be able to give an example of why e-greedy and greedy and pessimism can result in linear regret. I don't think you need to be able to do this for Gaussian rewards, but you should be able to do Thompson sampling for the case that we've just talked about, at least like sort of in pseudocode land. So if someone said like, you observe another count, what would your beta parameter be? And then also that you should be able to understand the UCB bandit algorithm as we've covered in class. So we've been building up all of these things to think about now how we can do exploration and data efficient learning for sequential processes. So next time we'll think about how to do this when we're in a standard decision process, as well as thinking about what do we do when we're in really large state spaces or really large action spaces, and how do we lift this all up for function approximation. I'll see you on Wednesday.